Welcome physics class. Our names are Alexandra and Angelina, and today we will be talking about Tacoma Narrows Bridge and its problem with resonance.
First we will be moving into resonance. Resonance comes from a Latin word resonantia, which means echo. Resonance phenomena happens when a vibrating system forces another system close to it to vibrate. The combined vibrations increase the amplitude of the object's oscillations, and the following phenomena only occurs if the first system is vibrating at the natural frequency of the second object, which means that if they vibrate at different frequencies, the resonance will not occur. Coming back to the natural frequency explanation, it is the rate at which an object vibrates when it is disturbed. Resonance is a common cause for sound production in musical instruments and for the sound of the sea when the seashell is placed at the ear.
The equation of the moment in resonance is as follows: x double prime times t plus k squared times x times t equals to the cosine of k times t. In resonance, when angular frequency omega equals spring constant k, the equation could be changed to x times t equals to t times sine of k times t over 2 times spring constant k. The graph which we added to the bottom of the slide is when the object is in resonance and its amplitude increases as expected. On the graph to the right of the slide, we showed that the highest peak, which is the resonance frequency, the least energy is removed by the damping force.
The normal resonance equation can be solved and broken down using three different methods. First one is explanational physical one, the ODs. The second one is the cookbook method, which has some limitations in usage and doesn't explain why it's done this way. Last but not least, there is an operator method, which can be impeccable sometimes. Solving this problem by the ODs method, where pdx equals g, gravitational constant, which is the force of gravity, which has to be taken into account when solving problems on the Earth's surface. G on the Earth is 9.81 meters per second square. Solved by writing the matrix of PD. Now we get the product of matrix. This is an A. A1 has a specific formula to solve this equation. Now we have the possibility to invert 1A, which is the product of a matrix, by inverting other A one after each other, and after such inversion we get a new constant. This is an example of matrix with randomly chosen numbers, and the way it is solved by firstly having two or more linear equations, then doing the matrix the way it has been previously explained. Here, as you can see, we have two lambdas, which means we inverted only two constant and can use it in further operations. There are two possible resonance equations, which look a bit different but come to the same result. If you really want to make sure the resonance is correct, it is advised to use both equations. Now we can start breaking down the components of the formula. First we have k, which is a spatial frequency of a wave, and is measured in cycles per unit distance. It is also often used instead of starting omega squared, which is a frequency. What is omega times t? It is a result of multiplication of angular frequency and time, which gets multiplied with the starting force. As you can see at the end of the second formula, we have a combination of time times energy per spatial frequency of a wave. And at the end of the first formula, there is a combination of an angular frequency times the time.
Examples in real life which vividly show the resonance phenomena include swings and musical instruments. In swings, you get a large amplitude when you push in rhythm, which requires the least amount of energy. In musical instrument, the vibrations which you cause the air to vibrate at the same frequency, producing the sound. Some negative effects of resonance include when soldiers are told not to march in unison on the bridge, as they produce a large frequency which will follow in large amplitude, and the following can destroy the bridge.
Now we will be talking about Tacoma Narrows Bridge. Tacoma Bridge was opened to traffic on the 1st of July in 1940, and it collapsed on the 7th of November in 1940, but it was closed prior to the collapse at 10 a.m. The bridge was connecting the Tacoma and Kitsap Peninsula, which are in Washington state, and it had the nickname of Galupangeri, and its oscillation started as soon as the bridge opened. The problem was the wind, as the wind of 6 kilometers per hour could produce oscillations. When it collapsed, the wind was 68 kilometers per hour, and the oscillations were 3 to 5 feet, and tilted for 45 degrees, which continued for 30 minutes before it collapsed in half. At that time, it was the third largest bridge, length of which was 5,939 feet, and it had two supporting towers, each 2,890 feet.
Now we will analyze how the resonance played its role in the destruction of a bridge. A 68 km per hour wind produced a fluctuating force which was in resonance with the natural frequency of the bridge. The following resulted in the resonance phenomena, and its amplitude was increased. Because the angular frequency was equal to the natural frequency, energy emitted on the bridge was of minimal energy, and the result were oscillations with large amplitudes which were increasing. On the graph on the right, you can observe how the resultant amplitude changes where angular frequency is not equal to the natural frequency. Continuing from the previous slide, the bridge was driven with right frequency, but the resultant force from the wind caused inadequate damping. Following the day when the bridge collapsed, the small oscillations became violent destructive torsional movements. Oscillations turned into two dominant twisting waves, which caused the bridge to collapse in the middle. Now that we know what happened, we will analyze how the collapse could have been avoided. When the bridge was being built, it was ready to withstand a wind at 161 km per hour, but only if oscillations were longitudinal. The torsional oscillations lowered the critical speed of the wind and resulted in torsional response, one of which is damping. On the bottom right corner, you can see how the torsional oscillations cause an increase in vibrational amplitude of the cables of the bridge construction.
Coming to the structure of the bridge, Tacoma Bridge was designed to be light, flexible, and lean, and as cheap as possible. No additional costs wanted to be made. But looking at the picture, it is seen that in usual bridge designs, the air is allowed to pass through, whereas in the Tacoma Bridge, air was expected to flow below and above the construction. The following made the construction extremely vulnerable to fast winds and winds in general. Before understanding resonance, bridges for heavy trains were designed based on arches, cantilevers, and trusses, and suspension bridges for cars, such as Tacoma Bridge, were built less strong, and scientists didn't understand the outside forces on the bridge, for example, resultant forces. Thank you for your attention.